So let's go through the methods. Let's start with Runge-Kutta. I'm not going to talk through Hoyne's method just because you'll have a chance to do it on your homework, and it's pretty much follows these other techniques. But if you do have questions on that, let me know. So let's talk through Runge-Kutta. Runge-Kutta, if you remember, is a fourth order technique. It is explicit, meaning we don't actually evaluate or we don't include temperatures that are part of the final solution in the formulation, meaning we don't say use the temperature at the end of the time step directly. We just predict it and then correct it later. So it's explicit, even though we're doing multiple estimates at different points in time. So let's go through this process again. If you remember, what we're trying to do is say, let me just make a note over here on the right-hand side here. So what we're trying to do is we want some function, and we're going to make this a vectorized function. That means the function applies to every element in the vector. So we want some function of the current temperature vector and the current time that gives us back dt, dt1, dt, dt2, and so on up to dt, dt, dtn. We want a vector that returns our derivatives. So the notation I'm using is if I have a bar over it, that means it's a vector. And it's a vector of the size of the number of spatial nodes, n. OK, so that's what we're going for here. So I'm going to make my first evaluation of the derivative of all those derivatives at the current temperature, Tj, and at the current time, time j. So if I do that, I'm going to call that AA bar. Right? AA bar is equal to my vectorized function evaluated at time j and at temperature vector j. So think about that. Make sure you kind of process the notation I'm using. I'm getting an estimate of dt dt's. Here, I'm calling that AA. To do that, I'm taking my vector function, f bar, evaluating it at my current time, tj, and my current temperature, temperature bar, j. So this is like information I'm coming into this time step knowing. So that's my first estimate. So that would be right here, right? AA bar. OK, then I step forward and I compute my estimated temperature. We're going to call my estimated temperature T hat. So that's going to be T bar j plus AA bar times delta T over 2. So what is that saying? That's saying I'm going from current temperature here, I'm stepping forward half the time step. And I'm going to make my next evaluation here at Tj plus delta T over 2. At that point, I'm going to evaluate the derivative again, and that's going to give me BB bar, and that's going to be F bar evaluated at Tj plus delta T over 2, comma T hat. All right, so I'm getting the derivative at the middle using my T hat that I just computed. And then I can step forward again. So when I step forward, I'm gonna reuse the notation like we did in the last time. I'm going to just keep calling whatever my current working temperature vector is. I'm going to keep calling that T hat, just so I don't have to come up with different names all the time. This T hat is different from this T hat up here, right? These two are going to be different. So my next T hat is going to be, where am I here? So next T hat is going to be T bar j plus BB bar times delta T over 2. So that's saying now I'm going to go back to the beginning using the derivative I computed here and try to take another step forward, right? So you're kind of jumping back and forth making these different estimates. So my next t hat is going to be again at the midpoint, but it's using the derivative that I computed at the midpoint as opposed to at the beginning. So here I have BB that I'm making the evaluation, and then we're going to have CC that is also being made at that location too. So CC is going to be F bar Tj plus delta T over 2 at the t hat, right? And this t hat is this t hat, which is different from that t hat, right? So we're just keeping this kind of running inventory of t hats, I guess. So CC is my next evaluation. I'm making it again at the midpoint here, which I noted up there, using the computed value here. So it's kind of, you get this recipe, and at one point you'll understand it, you'll stare at it long enough to understand it, then you just follow the recipe and you kind of forget it, right? Yeah.
In the code, would you have to name the t-hats differently?
Nope. You keep it the same, because it just reuses it. And you'll see that in the implementation is, I'll call this t hat, I use it once, then I reassign it to a new thing, t hat, use it again. You just have to like understand, or maybe better make a comment in the code that these are different things and they aren't preserved outside the function. It's just this temporary placeholder. And in fact, what you could do if you really wanted to make it clear, we've called it t hat just for the sake of clarity, I guess. But you could just make this evaluation in the function argument itself. So just get rid of the t hats altogether, put this whole thing right here, just as you are dealing with this here. Because ultimately, you're calling the function. We're doing it shorthand here, but you're calling this function using these arguments. OK, so that's CC. Take our next step forward. So that becomes t hat is equal to t bar j plus CC times delta t. So that step is taking the full step from the start to the end using the derivative CC that we evaluated at the middle. And then I make one more evaluation, which is dd bar, and that is f bar tj plus delta t at t hat. So this is going to be evaluated dd at the very end of my time step. And if you remember what RK4 does is that then takes all these different estimates and weights them together. So my actual step tj plus 1 is going to be t bar j plus all the weighted sum, which will be AA bar over 6 plus BB bar over 3 plus CC bar over 3 plus DD bar over 6 times delta t. So, yep, we're making our estimate, our actual step forward based on all these different estimates together, averaged together. So we can look at how this is implemented. Actually, what I should do is say what? So this is for j is equal to 1 to m minus 1, right? The second to last time step. Because at the last time step, you'd be stepping beyond your number of nodes if you went to all the way to m. So let's look at how this is implemented. OK, so we have RK4 here. And I'm going to look down at the code. So we're looking right here. So you can see how this is implemented. We have our loop that goes for j from 0 to m minus 1. So that's going to go from the first to the second to last time step. And at each of these points, I'm making my evaluation. So AA is my function at time j, at temperature j, and I'm passing my arguments that I've constructed. I get back a t hat from that by taking that derivative times half the time step plus the current temperature. Right? So you see how this works. You have t hat, you use that for the next evaluation, get your derivative, get the next t hat, use that, and so on, just as we said you would. And then at the end, we do the weighting. I guess I pulled the 6 out here, but it's AA, BB, CC, DD times DT over 6. And that's our actual step forward. So if we run this, we should see that it hopefully does what it's supposed to do. I haven't computed any error statistics or anything, but you can see it's stable. The solution looks the same. So what is RK for Bayou? Well, it gets you a more accurate solution than you would get for just the Euler's technique. So you can get a greater accuracy for the same number of time steps. Okay, yeah.
Is m minus 1 the last time node, or is it the second last?
It's, yeah, so the way Python works is you go from like the 4 statements. If you do 4, what it's saying is for I, if your index is I, for I equals the first thing until you're less than the last thing. So it would go from 0 up to less than m minus 1, which would be, the last index would be m minus 2, which is the second to last thing in the array.
Got it. Okay.
Yeah. So it's inclusive of the first thing and less than the last thing. Yeah.
In the code, what is that arg list thing that you're multiplying by?
Yep. So that's my shorthand way of passing in all the arguments that I want to. So where did I do that? Up here, I created a list of arguments that I want to go to the function. So that is all these things. If you look up at my function here, I'm asking for q dot, t infinity, all this stuff. So rather than like write that out every time, I just create a list here of the things I want to pass, and then I pass it as the function to the function directly. But the reason why you see the little asterisk in front of it is because what it's expecting is an expanded out list of these items, not a contained list, not a single structure. It expects all of them. So what the asterisk does for you is it expands out the list in place. Yeah, Nate.
You may have covered this the last time we talked about Roman Kutta, but what was how did you figure out what the weights are supposed to be for that? Was that kind of empirically figured out, or was there a method there?
That's a good question. I don't know how that was decided, other than the folks who derived it decided that was the right way to do it. But I think the general idea is that you have, let's see, let's go back down here, is that you have certain derivatives that you think are a better estimate. So the derivatives that are taken in the middle, BB and CC, are deemed to be of higher quality than AA or DD. So they're given a higher weight, relatively speaking. And if you just add up, right, if you add up all of these, and it adds up to 6, you have to divide by 6. So it basically comes down to the quality of the estimate of the derivative. Yeah.
That last node, is there any way to calculate for it, or is it just kind of like lost in calculation?
The last node in time. So by going to the one, so if you take your index to go up to the one adjacent to the last one, what you're getting is j goes up to the second to last one, but you're computing here j plus 1, right? So you're computing the last temperature here. What you're not getting is the estimates of dt dt at the final time step, but you don't need it, right? Because you're not stepping forward. Okay. Good. So that's Runge Kutta. We can talk through some other ones, which we'll do quickly here.